Okay, today we will be discussing about the applications of cryogenic technology. Okay, this is a very general topic. So there are a large number of applications of cryogenics. So we are going to talk about the applications of cryogenic technology. So what we will do is we will try to talk about, give an introduction to the historical introduction. So this is not anything new. You already know about it, but just we'll revisit just to say that these are the historical events. Okay. Then we'll discuss about the different cryogens. Normally, you come across nitrogen, oxygen, helium, and hydrogen. These are the main fluids which you normally come across. Okay, there are other fluids like, let's say, argon or neon, etc. are there, but then they are not used to large in quantity. They are used very less in quantity. So we will mostly talk about these four cryogenic fluids only. Then there are a number of applications in the area of space cryogenics. Okay. So you have applications of cryogenics in space. Okay. In space cryogenics, you will see applications are there as fuel, oxidizer, cryogenic stage. Okay. Then you come across space simulation chamber, etc. Okay. Well, we'll see all those details. Then in food industry, so you have cryogenics, its utility for food. That means storage of food products. Okay. So there are a lot of applications relating to that. So that we will see. Then there are industrial applications of cryogenics. So we'll see that. Biological applications, then applications in the area of vacuum technology, then superconductivity. We already seen some part of it. We'll see it again, no problem. Okay. And then there are applications for ground freezing using liquid nitrogen. Okay, you may be surprised. What do you mean by ground freezing? Suppose I want to drill a tunnel. Okay, then I need to cut open a chunk of the ground. So it is easily done by using a method of freezing the ground and then drilling it through. So that is an area where you can see. Then there are cryo-imaging. Cryogenics is useful for imaging. Okay, high resolution images can be obtained using additional use of cryogenics. Then machining cryogenics. Cryogenics useful in machining. Okay, hardening of material. Okay, so for example, I have already told you when we discuss about the material science that, for example, cryogenic treatment of metals, it is stainless steel, for example, it improves increases the martensite. Austenite converts to martensite. So once it is converted, then it becomes a very useful material and it is a very tough, okay, has a long life. Then cryogenic deflashing comes for rubber products. Okay, rubber products, the deflashing, that means removal of the flashes of the rubber components. Then cryo grinding conclusions we'll talk about. Okay, and some intermediately, for example, cryogenic shrink fitting, etc., will also be coming to be. Okay. So these are the various topics that we are going to go through in this lecture. Right? Okay. Let me say the following, that I am taken this particular part of the lecture from the Professor Rijo, who had already prepared this for applications. So I am mostly using his slides only. Okay. So any of the additional things which I have added, there are not many. Only one part has been added, and that too in the area of cryogenic treatment of metals. Other than that, more or less the entire thing is Professor Rijo's information what he has prepared for this, right? Okay, how cool is cryogenics? Well, it's quite cool, very low. So let's look at the applications of cryogenics. So you come across, for example, oxygen, nitrogen, argon, okay, helium, and things like that. So these are known as cryogenic fluids, right? They are called as cryogenic fluids. Okay. Now, this you have already seen. For example, whenever a cryogenic fluid is flowing through a pipeline, you can see the iced condensation, or you can say the frost appearing on the surface of the pipe, which carries the cryogenic fluids. So you can see here ice formation. Okay, it not only the ice, it is also consisting of carbon dioxide and water vapor. Okay, these are the things which are normally present. Carbon dioxide will sublimate, that means it will go into atmosphere, whereas the water will condense into, ice will condense to water. Ice will now melt off and then become water, and then water will be just dripping out on this, right? Fine. Now, this is a familiar slide to us because we know the temperature scale in Kelvin. So we know very well that 123 Kelvin or minus 150 degrees centigrade is a sort of borderline between the upper side, which is refrigeration temperature range, and lower side, which is correspond to the cryogenic range. And we know what is cryogenics, consisting of two Greek words, which is representing, okay, to produce the code, okay, the production of the IC code. That's what you have. So this picture nicely shows you the schematic of crystallites. Okay, lot of ice crystallites which are getting formed. So it gives you some idea of how the ice crystals will be formed, right? You see normally whenever the cryogen is poured from one container to another, you see a vapor cloud. Okay, you can see here the vapor cloud, and this vapor cloud is because of the water vapor that is present around that and carbon dioxide. So these are the things which cause the vapor cloud. So whenever there is a rapid evaporation, you will see the vapor cloud appearing on the surface, right? Okay, actually, if you look at the phenomenon of cryogenics, what sort of cryogenics people had in the earlier times, there was a demand for cold environment by the brewing industry as well as meat packers. Okay, so these were the two important applications in the early times. Okay, so for them, what they did was they traded in natural ice. Now took normally ice. So ice can be used for cooling the products. For example, the brewing industry can use ice as a coolant for the brewery products. Okay, and mostly the ice was also useful in chilling meat. Okay, all the meat packers, they used to use ice, okay, for storing the meat, etc. So this was the scenario in the early times. Okay. Then comes an important invention by James Dewar. This slide you have seen number of times. So James Dewar making a demonstration of his Dewar flask, nothing but a double-walled vessel. Okay, and in this double-walled vessel, the interspace is evacuated. So because of which it was able to hold the cryogenic fluid for long periods of time. So we have seen that the flask is able to hold the cryogenic fluid, and the reduced evaporation rate was approximately 30 times. So you will be able to see that there is a good amount of cryogen stored in the cryogenic fluids in the container, thermos container, okay, in this flask. So you call this as Diwar vacuum flask. So please remember, that's the name what you give for this. Okay. Now, this is one of the turning point in the cryogenics because people were not able to, store the cryogenic fluids. And earlier to this time, people had tried to liquefy, but it is becoming more difficult, especially if you go to cryogens, which are lower boiling points. That's more and more difficult to liquefy them. Okay. So this particular invention really helped to get to storing of the cryogenic fluids. That was one of the remarkable inventions of James Siva. Then comes another important invention, which is the helium liquefaction. This also we have seen. Okay, helium gets liquefied, and then this helium liquefaction was done by Professor Camerlingonus in University of Leiden. So he has been able to do this successfully. Okay, and now the whole experimental setup now remains there as an exhibit in their place, right? Okay. Then comes another important invention, which is by Samuel Collins to make a laboratory grade helium liquefier. Okay. See, almost all the liquefiers currently made by various companies, they exactly follow these procedures which are given by Samuel Collins. The heat exchanger is one of the marvelous, structures which were done by Samuel Collins, and this is one of the beautiful inventions. So helium liquefaction allowed people to carry out experiments right down to very low temperature, that is 4 Kelvin, right? That was the possibility for them to do this. Okay, so this is another important invention in the area of cryogenics, right? Okay. Okay. Now, looking at the applications, there are a number of applications. Superconductivity, the superconducting levitated trains. Okay, you can see here the superconducting levitated trains, and this image shows you the high temperature superconductor using liquid nitrogen. Okay, the superconductor is floating in the air. So it is the magnetic levitation what you normally see. Now, where is the cryogenics needed? Where all cryogenics is needed? So it is needed for space cryogenics, cryobiology, cryonics, cryopumping, cryotherapy, cryosurgery, all industrial applications, cryoground freezing, and then cryopreservation, okay, cryoimaging, etc., etc. There are some many fields of areas which are using cryogenics. Okay, so let's look at some important applications of this cryogenics. What happens to materials? The property of material changes, that we know. At low temperature, solid, liquid, gases. Generally, as we know, first of all, as you go to lower in temperature, you form the liquids. And then if you go further low in temperature, you get a solid state. So there are a number of properties of material changes. For example, we know that material become brittle, like glass and things like that. Now, if you see the various cryogens that are available, you can talk about helium, you can talk about oxygen, you can talk about hydrogen, and nitrogen. Okay. So these are the various cryogens that one can see, okay, which can be used for low temperature applications. Okay, normally, there is a particular boiling point for every fluid, and the boiling point is corresponding to uh, the temperature at which the cryogen boils and its atmospheric pressure is 1 bar. So that is the sort of nomenclature for this, right? So you have a certain boiling points, etc. The property what you see here, for example, in liquid helium, it is what is called the film flow. The helium is actually moving out, superfluid helium moves out as a film, then flows down, okay, like a droplet. Okay. So that is what you see. Liquid oxygen is somewhat slightly bluish in color. And what is shown in the third slide as somebody pouring out, it is actually liquid nitrogen. And of course, if you take a bigger container, you can also pour other larger quantity of cryogenic fluids. Okay. Where are the applications? Now, if you look at the cryogen, each cryogen has got certain applications. So we can talk about the cryogens like nitrogen, oxygen, argon, helium, and hydrogen. These are the various cryogenic fluids that one normally encounters. Nitrogen being inert, and also the availability of nitrogen is very high, because of which the applications of nitrogen are many. Biology, medicine, steel industries, fertilizers, then food processing and preservation, okay, firefighting in mines and forests, then chemical industry, then high vacuum production. Vacuum technology is one of the important areas. This we have seen already. Then fabrication or production technology, okay. Then rubber recycling, bomb disposal, then archaeological specimen preservation. All these things are used using hydrogen. The next important thing what you see is oxygen. Oxygen is used in steel industry. There are a lot of medical applications. Then sewage disposal, deep sea diving, and also as an oxidizer. So oxygen is the another important candidate. Nitrogen boils at 77 K, oxygen boils at 90 K, both at atmospheric pressure. Argon, for example, argon lamps, then TIG welding is the utility for argon-based weldings. Okay. Then you have ultra low temperatures, helium cooling, helium-1, helium-2, helium-3, and helium-4. Out of this, helium-1 and helium-2 are two different states of helium. Liquid helium remains as a normal fluid, and then it also remains as a superfluid. Okay. The state helium-2 refers to only the superfluid state. Then we have hydrogen. Hydrogen is being used, for a number of applications. Okay, we use hydrogen for the space applications, okay, as a fuel, and then also oxygen as an oxidizer. So these are the applications of the cryogens like nitrogen, oxygen, argon, and helium, and hydrogen, right? Okay, let us look at the applications one by one, okay? First, we'll see the application relating to space cryogenics. Basically, rocket propulsion, then cooling of sensors, then space simulation. These are the important applications of the space cryogenics, right? Okay. So let's see one by one. So we'll start with the rocket propulsion. Now, this picture, whatever you are seeing here, is from probably the NASA. So you see here the cryogenic fluids being used as what shall I say, as fuels and oxidizer, because you can use hydrogen and oxygen combination. Again, you can use this. So the cryogenic fuels, what we normally have for rocket propulsion is liquid hydrogen, liquefied natural gases, and then liquid oxygen. So this is for the rocket propulsion, people use this. It is well known that hydrogen and oxygen form the fuel and oxidizer to launch the vehicles. Why it is used? The reason simple is it has a very high impulse, high specific impulse. So it is so many kilograms of thrust produced per, let's say, kg of the propellant and so on. So the value is approximately double in the case of cryogenic fuels and compared to the alcohol oxygen mixture. So it's only 250 and the other one is 500. Okay. Now, storage and handling of liquid is most easiest method, and therefore people use large quantities of cryogenic fluids. Okay, and the cryogenic fluids are used in the liquid state form, right? Now, if you look at the rocket propulsion requires you require a fuel, you require a oxidizer. So in the case of fuel and oxidizer, what they normally use is liquid hydrogen as a fuel, liquid oxygen as the oxidizer. These are the ones. So you can see the a cryogenic engine here, along with appropriate, sorry, there are a lot of appropriate systems which are added on to that. Okay, for example, what is not shown here is the cryogenic tanks. Okay, so this, what you see here is the engine. Okay, the space propulsion, rocket propulsion engine, this one. So this is the one which will give you a thrust for the rocket to go upwards, right? So what does it contain? All these things. Okay, basically it contains, other than the cryogenic fuels which are stored above, there are some pumps, okay, which pumps the fuel. And then there is some ignition source that gets ignited. And once it is ignited, then automatically it passes through this chamber. This is a chamber which is sort of pre-cooled initially with the cryogenic fluid itself and then goes upwards. Okay, so that you have this, pre-cooling of the nozzle zone carried out. Okay, so you can see here the structures. Okay, this is the actual photograph, and this one shows you the internal structure. In the NASA related activities. Okay, it is some systems which are shown here. Okay, the letterings are too small to study. Okay, you can see here in this picture the rocket propulsion which is being carried out in the laboratory. Okay, where you can see beyond the so-called cup arrangement, you have the ignited flame which is flaming downwards. Okay, so you see here this is the flame. Okay, so how does it happen? So first what you do is you have huge tanks for the cryogenic fluids, both for oxidizer tank as well as the fuel tank. So hydrogen, as you know, the density is very less. So you have the hydrogen tank above, and then below that you have the oxygen tank. Okay, these are the two types of tanks which are present. Oxidizer. So if you, for the pump, you want the oxidizer, then you draw the liquid from the appropriate liquid pipeline will be there. So the liquid will be drawn by this particular pump. Okay. Then you have a fuel pump, that is hydrogen is being brought in here on the opposite side. Okay. And what happens is the exhaust of this are combined together to make a gas generator, and then a part of it enters the chamber. Okay, and in the combustion chamber, it gets ignited, and after the ignition, then you see a small part of it, the cold vapor part, again returns back a number of times so that it pre-cools the combustion chamber. Combustion chamber will be very, very hot. So you need to cool it. So this pre-cooling part is already done in this heat exchanger. Okay. Now the ISRO has a number of launch vehicles. So this is just a bird's eye view of the some amount of ISRO space launch vehicles. So SLV is actually space launch vehicle, SLV. Okay. So there are a number of categories of SLV-3s, for example. Say SLV-3 typically is a height of 22.7 meters. Lift-off weight is about 17 tons. Then it is entirely solid. And the payload mass is about 40 kgs. And it orbits is low Earth orbit. That's the sort of orbit what it chooses. Okay. Then you have what is called ASLV. It's all solid launch vehicles. Okay. That is also there. Okay. That has the lift-off weight is almost double. So it is slightly more than double, about 39 tons, etc. And the payload mass is 150 kgs. And it is useful for, orbit will be low Earth orbit sort of things will be there. Now, the next type of system which ISRO has been able to make is what is called the PSLV. The PSLV is Polar Satellite Launch Vehicle, PSLV. And there you can automatically see the height is also increasing, and the Polar Satellite Launch Vehicle can have a payload mass of 1,800 kgs. Orbit will be 475 kilometers, and sun synchronous polar orbit is what is chosen. Okay, and 1,300 kilogram inch geosynchronous orbit is what is chosen for this PSLV. Okay, next comes the one system with the cryogenic fuel, which is GSLV, Geostationary Launch Vehicle, geostationary. Okay, that is actually the one which is having about the liftoff engines have at 414 so many tons of the liftoff weight. Okay, propulsion is having solid, liquid, as well as cryogenic engine. Okay, these are the three things which are there in GSLV. And the payload mass is about 2,200 kg. Okay, it undergoes a geosynchronous transfer orbit is what is normally suggested for this type of launch vehicle. Then, of course, GSLV has several models. This is Mark II. You have a Mark III version. In the Mark III version, liftoff weight is somewhat increased, and the propulsion is solid, liquid, and cryogenic fuels. And the payload mass is about 4,000 kg. It is again geosynchronous transfer orbit where it can fly. Okay. Okay. Now, space cryogenics, GSLV spacecraft design. I would like to just to show you a picture of the GSLV spacecraft here mounted for just prior to launch. And you have actually there are some data are given here in this one. Okay, the overall height of this GSLV is 49.13, and the liftoff mass is about 414 tons, and liftoff thrust is approximately 6,773 so many kilonewtons, and it has 3 stages. Okay. So this table gives you all information regarding the first stage, second stage, and third stage, and what sort of the material is used for the oxidizer as well as fuel. That's what is here. There is also some, so if you, for example, if you take the first stage strap-ons, you have what is called UH25 and N2O4, which is UH25 is UDMH and then hydrazine hydrate. HTPB, that is your high density, hydroxyl terminated polybutadiene. That is the another type of fuel what is being used. So in combination with so this is normally used the coast stage, one can use it. And there are the second stage is generally UH25 plus N2O4 combination. The last stage is generally the cryo stage. In the last stage, you have the liquid hydrogen and liquid oxygen as the fuel and the oxidizer in the system. So here, for example, a launch vehicle has been just mounted in the zone where it has to be about to be lift off. Okay, so maybe Sriharikota or somewhere where it has been taken. Okay, there is India has also proposed a manned moon mission that they are planning, and it will be attached to one of the heaviest launch vehicle. Okay, and that system, more details are shown here. So what is there on this topmost zone is expanded like this. And if you look at the internal parts of this one, then you find there is a three-member crew can be there in this one, visiting moon and coming back. Okay, there is a cutaway view showing the 3-person crew and the environmental controls as elements. So this sort of system has been designed. This will be launched by ISRO at some time. So far, we have seen rocket propulsion. Okay. Next, we will see the cooling of sensors. Okay, that is another important area in the space cryogenics itself. Okay, you need to cool sensors. How it is being done, we'll just have a look. So one other thing why we need to cool in space is because you have many telescopes, detectors, cold probes, etc. As you lower the temperature, the noise reduction is significant. So because of this noise reduction importance, you use this sort of small cryocoolers which can work at very low temperatures. Okay. For example, the person is holding the Lockheed Martin Space System micro cryocooler for the Jet Propulsion Laboratory, USA. So you can see this is the helium compressor, and this is the connection to the this is the cryocooler part, and you can see the cold end at this end. So everything is fitting in a very compact manner into the hand. Okay, there are slightly bigger systems also available, but they look something like this as in the photograph. Okay, what sort of cooling requirements are there in that is provided in this table? Radiator operating at 80 Kelvin, the heat load is typically 0.5 watts. It is quite reliable, low vibration and long lifetime. But it complicates the orbit. So normally, because in some cases, you will see the light entering. In some cases, light will not enter. So you have to take the right radiation zone for that. Okay. Now, if you look at the cryogen, normally it is 4 Kelvin that is directly used with the cryogen. You can use 4 Kelvin, you can get, but the heat lifted by that is 0.05 watts, stable, low vibration, but then it's a very short lifetime, outgassing issues. Okay. And sometimes, you require to have large quantity of cryogenic fluid. So it's a massive system possible. And many times it's quite complex because it's very expensive also if you use the cryogenic fluids. Stirling type of cryocoolers are useful at 80 K, about 0.5, 0.8 watts, then efficient. And so this is a advantage is that it's quite efficient. Disadvantage is because of the motion of the displacer piston, you always have a certain amount of vibration. Coming to second stage stirling, which operates up to 20 Kelvin, but cooling power may not be very high, 0.06 watts. So you get an intermediate temperatures, and many times these are specifically developed for the application. Pulse tube systems are fairly well developed, and typical temperature 80 Kelvin, you get a cooling power of 0.8 watts. Or if you go to Peltier type of coolers, you operate at a very high temperature of 170 Kelvin. The cooling power requirement is 0.01, 1 watt sort of thing. Peltier coolers, 170 Kelvin, 1 watt. So it's lightweight, at the same time high temperature and low efficiency. Joule-Thomson coolers are there, Sharpson coolers are there. I mean, these are some of the coolers which are more or less vibration free completely. Okay. Sharpson coolers can give you at 10 Kelvin about 0.1 watts. Okay. Whereas direct cryogenic fluids can give you a good low temperature performance. Then the reverse Brayton type of cryocoolers, 65 Kelvin operating zone, 8 watts, high capacity. It has high capacity advantage, but it's somewhat complex. Adiabatic demagnetization refrigerator systems, 0.05 Kelvin. Yeah, we are quite low in temperature. And the cooling power heat lifting out of this is 0.01 milliwatts. So it's not a very large wattage. And there are, if you want to go to very low temperature, this is the only way out. And large magnetic field can be harmful for these sort of systems. Now we talk about the space simulation. Okay, what are space simulation? How is space simulation taken care of? Okay, what happens in space simulation like this? You have a satellite, etc., which is developed in the lab, but these satellites, etc., have to be put in space. Okay, and when you put it in space, it meets all the space requirements. Okay, it has to operate at very low temperature. It has to operate at extremely high vacuum environment. Okay, so the testing of the components, etc., have to be done in the space environment in the laboratory level. So, for example, here you can see a system. They are a sample chamber in which there are radiators through which the cooling is being done. It is done by there are methodologies to achieve whatever temperature range you want here, either by circulation of liquid nitrogen or by using an appropriate cooling arrangement to produce liquid nitrogen temperature. Now, the actual temperature, if you are really interested, it should be obtained by cooling the walls by using liquid nitrogen and liquid helium. vacuum level of 10 to the power minus 14 torr can be obtained by cryopumping, and that again using liquid helium. Okay, so this space simulation chambers are something which are very useful, okay, for the practical applications. Okay, I am just showing you a space simulation chamber. Say, for example, the space simulation chamber can be fairly big in size, number one. Okay, and you can make a lot of visual observations using quartz windows and Pyrex windows and so on. And you can have a, optical, liquid cooling and warming arrangements. Okay, double layer type of thing are possible. So you can have cooling arrangements, appropriate cooling arrangements are possible with this one. And then there are a lot of measurement instruments, like for example, hygrometer or flow meters, etc. All those systems are also housed along together. Okay. Now, the space simulation chamber has to be built according to the requirements of people. Okay, so we'll now move on to food cryogenics. Okay, what about food cryogenics? As I mentioned, the cryogenics requirement for food is essentially to keep it in good condition, okay, cryogenically frozen, and either you store it or you keep it in a good condition. Okay, you will thaw and then start utilizing and so on. Then so how exactly you do it? That's what we'll now see that. First, we'll talk about the cryofreezing. Why cryofreezing is required? First of all, we know that if you keep the food in the ambient conditions, the food gets spoiled. Okay, after some time, the food is not something which you can eat very well. What are the causes of the food getting spoiled? Microbial, maybe bacteria, mold, yeast, etc. Or there can be chemical reactions by enzymes, exposure to oxygen and light. They accelerate. Then there are also situations where physical damages due to bruises and cracks and so on will happen. Okay. Now let us look at cryotransportation. What is cryotransportation? That means you have certain items which are packed, okay, and let's say frozen. After doing the cryofreezing, you will be able to transport it to. So cryotransportation is needed after the cryogenic freezing. Okay, so we'll see what are the things like that. Now you can see here trucks, huge trucks having liquid nitrogen, and then there may be arrangements for cooling all the objects, etc. Okay, but one of the thing is whenever particularly you want to cool meat products, etc., using cryogenic cooling, then you should ensure that you have a faster cooling so that you will have only small ice crystals formed. It should have a low drip loss and it has a better taste and flavor. Okay. So this is essentially for bulk. Whenever you have a bulk arrangements, then you follow these other things. So internal quick freezing means no additional freezing is required. The freezing load, the better consumer acceptance and better temperature control is possible if you do the individual quick freezing. Okay, let's come to cryo grinding. Cryo grinding is another important area. So what we can do is we can take some material and grind it at cryogenic temperatures. So this has been done already for spices and herbs. So, for example, why do we need to do that? For example, if I try to spice, if I try to grind the spice, you can see a flavor. Okay. These flavors will be there only for a short time. Afterwards, they will disappear because they are coming out of certain oils, which are called etheric oils. And these etheric oils, uh, they have a low boiling point and therefore they vaporize. Okay. So to make sure that etheric oils are present in the spice, you have to cool it to cryogenic temperature and then do the grinding operation. So during that process, the spices do not lose the cryogenic, do not lose the so-called flavor. Okay. So what happens is it is able to take care of the cryogenic grinding, is able to take care of the storage of the volatile substances within the powder, and thereby the aroma and flavor is not lost. Spice like sesame release some oils and makes it difficult to grind also. It combines with oxygen in some cases and poor quality. The air dried prior to cryogenic cooling to avoid excess moisture entrapment. The less quantity only is required, namely 100 grams to 10 grams only is required for special materials. Okay. Okay. So now we are going to talk about industrial applications on cryogenics. Okay. So what are the industrial applications on cryogenics? We have seen some of the things already, but still we would like to just go through that a little more detail. One is, of course, cryogenic distillation. This we have seen. The distillation process in which the nitrogen and oxygen get separated. Or multiple, in many cases, there are two different fluids have their very, very close tolerances of their, say, liquid nitrogen and oxygen. Liquid nitrogen oxygen, their boiling points are fairly close. Okay. Say 90 Kelvin and 77 Kelvin. So because of these reasons, you have a special way of distillation, that you make a distillation column in which the nitrogen will flow from the top and the oxygen part will go from the bottom. Okay, and then they get separated. This we have seen already. Okay. So there is a cryogenic distillation is one of the important processes. Then LNG processes, helium production is something very important because you can reach a very low temperature. Also, cryogenic carbon capture, that's another important area for the industries to pursue. Okay, what is cryogenic distillation? It is the production of gas from atmosphere by cryogenic separation. Okay, LNG processes, for example, conversion of natural gas into LNG. Okay, or reliquefaction of boil-off gases, regasification of LNG, etc. Okay, helium can be produced from natural gas, but then whenever you want to have a high purity helium, you must use cryogenic fluid. Okay, and for example, whenever you have cryogenic carbon capture, it cools the CO2 laden flue gas to desublimation temperatures to separate the solid liquid carbon dioxide, which is compressed and disposed. Okay. Now let's look at the cryogenic air separation. What you see in this picture is world's largest oxygen production unit, and this is in a place called Secunda in South Africa. The capacity is only 45,000 tons per day. So it's a fairly large percentage of production in terms of the so many tons. Okay. Now let's look at the LNG process. Okay. converts from natural gas to LNG and reliquefaction, boil off gases, etc. That's what we are going to look at. Okay. So LNG technology is a very important technology. We already see that LNG technology is there. LNG technology will give you a clean fuel, first thing. Okay, the impurities will be very less. And on the other hand, if you have the CNG sort of system, then you need to compress the gas up to some level and thereby perform the experiments. Okay. Okay, this slide shows you one of the huge plants available for LNG. Okay. Now the largest LNG producer of the world is about 37 million tons per annum. You call it as RAS gas of Qatar gas. So there are different gases which names are known, and you can see the production LNG large production zones are shown here. They're all split. They're all mounted on either at the ground level or on transport containers, etc., appropriate sizes, so that it becomes useful for the user. Okay. Okay, next one is helium production. It's separation from natural gas, purification, and also distributed using cryogenic fluids. Let's see how exactly they done. Now, the source for helium is actually only the natural gas. Okay, the atmospheric atmospheric content of helium in the atmosphere is only 6 parts in a million. Okay, it's a fairly small quantity. On the other hand, helium can be extracted from the natural gas sources when they extract the oils and things like that. There you can separate it and you can get a good percentage quantity of this is available there over there. Okay, so it is possible to do that. The production plant, what is shown here in this plant, it is the air liquid plant at a place called Ras Laffan and in Qatar. Okay. So what it produces, it's about 38 million cubic meters of helium per year. So you can imagine the quantity of helium that's being distributed. It's such a large quantity of it. Okay. Now we come to the last part where cryogenic carbon capture. Normally you get a CO2 added flue gas. They normally come out of your the cryogenic systems, and these things, the flue gas is you desublimate. That means you cool it. You can do the desublimation, bring it to desublimation temperatures, and thereby you will be able to produce the solid and liquid carbon dioxide, which is compressed and disposed. Okay. This is the cryogenic carbon capture. We'll see a little more detail. So industries on cryogenics, they use cryogenic CO2 capture, CCC. It uses a fail change to separate CO2 and other pollutants. What normally done as far as CO2 is concerned, it is cooled up to minus 140 degrees centigrade and then desublimate. So what will happen is CO2 will remain as in the cold form. Okay, it will be more like a solid, but the CO2 cooled to minus 140 degrees centigrade to desublimate. Solid carbon dioxide now gets separated from the remaining gas and then pressurized, melted, and delivered at a higher pipeline pressure. Now the gas remains nearly pure nitrogen and it's released to the atmosphere. So generally, this is what is normally done in the cryogenic CO2 capture. Right. This is an indication of what exactly is being done. We start with the flue gas at this point. Now you desublimate. When you say desublimate, you are trying to reduce you go from the gas state to the solid state. See, sublimation is some solid state to the gas state. Okay, you have to add the heat. Now, when you do the desublimation, you remove the heat. And then it reaches the pressurization stage. Again, you melt it off and then you get the CO2 part. Okay. So this is the way in which the cryogenic CO2 is captured. Now, many chemical reactions like those used to produce the active ingredients for the popular statin drugs, it occurs at a low temperature and approximately minus 100 degrees centigrade. Special cryogenic chemical reactors are used to remove reaction heat and provide a low temperature environment. See, many products are involved. For example, biotechnology products, vaccines, okay, and they require the sort of cryogenic cooling. Okay. So these vaccines require nitrogen in the blast freezing or immersion freezing systems. Also, to produce medicines, especially used to manage high cholesterol. So you can also produce medicines using the which are needed for the high cholesterol control. We can use this arrangement. Biotechnology products require the chemical cryo. Now we come to cryobiology. I think what we will do is we will try to take a break for about 10 minutes and then we'll come back. Is that okay? Rahul?
Okay, sir.
We'll take a small break. We'll come back and then we'll restart the system. Okay. Okay.
Okay.
We'll stop here for a while. What's the time now?
8:51.
Okay. So we'll stop here. We'll come back at 9 o'clock. Is that all right?
Okay.
Okay. We'll come back at 9. Hello, welcome back. Are you people are there?
Yes, sir.
Yes, sir.
Shall we start again? Is it okay? Okay. Okay, I'm going to discuss with you the applications relating to the cryobiology. Okay, first of all, you can do the preservation, cryopreservation. Okay, you can take preservation of salmon, bovine or human, then blood, tissues, then bone marrow, okay, microorganisms or complete organs. All these things can be preserved at cryogenic temperatures. Okay, then next we'll move on to cryosurgery. Say, for example, you can use cryosurgery for taking care of blood loss during the surgical process or removal of cancer or cancerous cells, etc., skin diseases, then cataract, piles, Parkinson's disease, etc. These things are possible under cryosurgery. Then you can also use cryogenics as a therapy. That means you can use it for, let's say, to give a feeling that cryogenics is good for you. So you can think of, for example, a muscle healing, or you have a nitrogen environment so that you think that the pain is relieved, or to reduce the inflammation. All those things are possible under the cryotherapy. So one by one we'll see. First we'll start with the cryopreservation. So what do you do in cryopreservation? So in cryopreservation, the cells and tissues can be kept indefinitely in a state of suspended animation, okay, and by storing in liquid nitrogen. So you have to store it in liquid nitrogen for any length of time. So they are in a state of suspended animation. That means the reaction rates become so small that there is no, it is getting totally preserved. No decay is possible. Many times cell death can take place, okay, during the freezing or the thawing. That is, if you are doing the freezing, you can expect the cell death, or at the same time, if you are warming up, then the cell death is possible. And still there are people trying to understand what's really happening, why the cells die. Okay, so it's a topic where a lot of research is going on. Okay, there are some issues relating to the cryopreservation. One is solution effects. As the ice crystals grow in freezing water, all your cells are in a liquid, and that liquid most of the time it is water. So solutes are excluded, okay, causing them to be concentrated. That is, see, essentially your system has, it's like a more like a solution. So, and when you start freezing the water very rapidly, then the solutes get excluded out of that. And this causes, the solution become very concentrated now. Okay, that means you have more amount of salt for a given volume of solution. So it becomes more concentrated in the remaining liquid. Now, this high concentration of the solutes sometimes damage the cells. Okay, so that is one of the effects of solution. Then sometimes it is possible that there are ice formation happening in extracellular zones. When tissues are cooled slowly, water migrates out of the cells. Okay, and ice forms in a zone which is extracellular, that is the outside cellular area. Okay, too much, so there the ice is formed. So too much extracellular ice formation also causes mechanical damage to the cell membrane, and because of crushing, because ice now occupies more space. So therefore, it tries to crush the cells. Then there is an effect of dehydration because migration of water causing extracellular ice formation can also lead to cellular dehydration. That is, from the cell, water is removed. So what it means, it dehydrates. Okay, the associated stresses on the cell can cause damage directly. Okay. What about intracellular ice formation? When some organisms or tissues can tolerate some extracellular ice, any appreciable intracellular ice is always fatal to the cells. That is, the ice formation within the cell is also not good. It's sometimes dangerous. Okay. What is the solution for the cryopreservation? What one has to do is you should freeze the cells and thaw it with very fast rates. Okay, so you should do it at a very fast rate. That is what one has to do. So in other words, one should follow a very strict temperature time graph. It should follow that way. But that may not be always possible. So obviously, what one does is you add additional chemicals such as glycol, DMSO, etc. And these are known as cryoprotectants. That means they protect the cells of the cryogenic fluids. Okay, so those things can be used for the freezing of the cells and thawing. So a lot of applications are there. Human erythrocytes and platelets you can do this way. Or for example, applications in the bull semen area, cattle and other livestock embryos can be stored. Then eye cornea and skin can be preserved. Many bacteria and fungi also can be appropriately preserved. Okay. How do you store making cryogenic storage? For example, if you want to store blood, okay, the blood can be stored in the cryogenic fluids. Okay, cryogenic fluid you can take, and then blood can be stored in the cryogenic fluids. You can also, there are a lot of challenges, of course, the human white blood cells. So if you want to store or big organs, etc., like kidney, heart, and things like that, there is always a temperature non-uniformity because of the size and poor thermal conductivity. Okay. So in such cases, mechanical damage caused by the unequal contraction of different components of heterogeneous material, okay, that needs to be addressed. Okay. That certainly one has to worry about that. Okay. What about the preservation of bull semen? So one normally uses artificial insemination. That is, artificially inseminate a bull, the bull semen into the cow or the other female part. So what happens is you can inject into the female reproductive tract, okay, at the appropriate time with the help of instruments, and semen is inseminated into the female directly into the cervix or uterus by mechanical methods. Okay, so this is one of the cryopreservation of the bull semen, and the utilization to artificial insemination is something which is very important from the animal husbandry point of view. So what are the advantages? For example, the number of cows mated with one bull can be as high as 2,500. Okay. And selective breeding is possible. Cost and danger of keeping the bulls are eliminated. You don't have to keep so many bulls. So all that you require is the bull semen, which you will be using for your cow. Okay. Disease spread through the natural mating can also be eliminated or controlled. And transplant of eggs or ova from superior cow can be transplanted to inferior ones. So it is now possible to do. Okay, we come to next, the other type of preservations, like for example, blood tissue, bone marrow, and other thing. Let's try to consider that. Okay, after this is over, so we can talk of cryosurgery. Okay, I mean, in the cryosurgery, what is normally do is the live tissue is first frozen. So, for example, I have a probe here, and using the probe, I have a liquid nitrogen which is entering at the other side and then gradually coming out. And this makes a small jet and then falls on the patient's, say, let's say the live tissue, whatever the area is. So this tissue is now frozen. Okay. And when you are freezing the tissue, surrounding cells also will get frozen. Okay. For example, the surrounding cells zones up to 1 to 5 mm halo is formed around your location, and they get the ice will be formed in those zones, right? Okay. So what really happens is your cells are made to die in the zone. Okay. And its effect is that another 5 to 8 millimeter uh, uh, ice formation is also there in that case. Now, the blood supply to this tissue which is frozen is not there. Now it is stopped because of it is frozen. So the cells now, the whatever cells you are frozen, it will die due to the lack of oxygen. So again, when you thaw it back to the normal conditions, what will happen? The tissue now will change its conditions. It will turn into a blister, and then slowly you have to eliminate the blister by using either a scab, or sometimes you have to get it released or removed. Okay, that needs to be done. So in the cryosurgery, essentially you are freezing a certain zone, and then effect of it is it locates the surrounding areas are all converted to ice, right? Okay, the cryosurgery can also be done in other parts of the body like skin, warts and cancer, eye. You can use cryosurgery for removal of cataracts. Brain, Parkinson's disease can also be using the cryosurgery. Gynecology people use cryosurgery. Internal injury also can be using cryosurgery. So essentially, you require a spray arrangement for cooling the specimen. Okay, so that cryotherapy, for example, it is shown here how exactly it is done. Now, what about cryobiology? Now, the liquid nitrogen is used on a cotton swab. LN2 can be cooled using a metallic cold finger, or you can also use a cryo tip. In fact, we are going to discuss about the cryogenic freezing. At that time, we'll discuss about this in little more detail. Okay, you get essentially nitron N2 or N2O operated cryotip. So you get a cryo spray. Okay, instrumentation to monitor the growth of the ice ball is needed. Okay, and so when you do all this, then you have lower chances of infection, the smaller or no incision in the process. Person need not stay in the hospital for long. Okay, it's again a better cosmetical approach to the problem. Okay. What about the problems? The problems involved are how do you control the ice formation? That is something which need to be really controllable. These are the important things to be taken care of. Okay. So let us talk about the cryotherapy. what is normally cryotherapy? Cryotherapy means you are using cryogenics as a sort of treatment for a disease. Well, there is really not much of a disease which it can cure, but to go to low temperature environment, okay, which you compared to our conventional ambient environment, you go to low temperature environment, that gives you a medical therapy. So it can be used to treat a variety of tissue lesions, and then you can think of having a effort to release muscle pain, sprain, etc., etc. A new weight reduction also is possible. So in other words, cryotherapy means people try to think cryogenics is a way of giving you a happiness that is for your rest of your life, let's say. So this is one way of doing the getting to cryotherapy. Okay. Okay. Now let's come to cryonics. Cryonics is what? Cryonics is that you freeze a person and convert it to almost a mummy. Okay, that's what you do in cryonics. Okay. And it was first proposed by Robert Ettinger and inspired by Neil R. Jones' science fiction story, that Jameson satellite. So what people do is that try to almost freeze a person in cryogenic fluid. That's what exactly is being done. The human breakthroughs in technology as one day can make it possible that for physicians to repair the brain and revive someone frozen in the past. So essentially you are trying to get back a fellow back into life. Okay. A couple of 100 patients are already been cryopreserved, while Ettinger died in 2011. He was also mummified, so to say, cryonically treated. What is the process? The process, briefly, after being pronounced dead, the patients are injected with the antifreeze compounds called cryoprotectants. And using the cryoprotectants, the body will not decay, okay? And then now you lower the temperature of the body slowly. Eventually, the patients are cryopreserved at liquid nitrogen temperature or even at a much lower temperature. Okay. It is hoped that sometime a person may be revived back to normalcy. Okay, the dead persons can come back alive after some time. Now, the cryonics, as you can see here, this is an advertisement for cryonics. It's called Life Extension Foundation. Okay, so you can see here the costs involved. It's phenomenal. $200,000 for whole body cryopreservation, which is about 1,15,000 to the patient care fund. Another 60,000 is for cryopreservation. Remaining 25,000 is for the CMS fund. So this is a way of collecting money for giving you a life extension. There are also other forms of preservation. Almost about $80,000 for cryopreservation, neurocryopreservation, about 25,000 for the patient care trust, and about $30,000 for cryopreservation, about $25,000 for CMS fund. Okay. Now there are these type of things. A lot of people are interested these days. They go and be there, get a feeling as though they have been preserved at low temperature. So they become, mentally they start feeling somewhat better. Okay. Now I'll come to another important area, which is cryogenics and vacuum technology. We have seen the importance of cryogenics and vacuum technology yesterday on the last class. So vacuum can be created, we have seen essentially in two ways, either the positive displacement, removal of gas molecules from the container physically, or you can also immobilize the gas molecules that immobilize the gas molecules by adsorption, either physical adsorption or chemical adsorption on a matrix, etc. This we have seen. See, the main advantage of the vacuum created in this manner is extremely clean vacuum, high pumping speed, and moderate cost for such cases. So, cryopumping is one of the important effect which is required for industrially and also scientifically. Use of cryogenic temperature is to produce vacuum, and removal of gases via a cryogenic temperature, either from a flow stream or enclosed without necessarily resulting in a vacuum pressures. Application in fusion energy research, space research, high energy physics, semiconductor production, all these areas, they use cryopumping. Okay. Now, cryopumping is a process in which the gas molecules are all sort of condensed, okay, on a specific surface before it starts going to the low temperature. Okay. Freezing of water, CO2, the temperature there is around 80 Kelvin. Freezing of nitrogen, oxygen, argon at temperature of 4 to 20 Kelvin. And also, for example, absorbing helium, hydrogen, or activated carbon, for example, T equal to 4 to 20 K. That you can produce very good cryopump using these sort of applications. Why do you need to have a clean vacuum? It is because it is needed under manufacturing of chips, okay, squids and other superconducting devices, space simulation chambers, etc. All these things you require this cryopumping. What about superconductivity? We have seen superconductivity and applications. Superconductivity is a phenomenon where the resistance suddenly drops to zero for a particular material. That particular temperature at which the resistance drops to zero is what's called the TC. TC, transition temperature, or TC, which you have to, at that particular temperature, the resistance suddenly drops to zero. Okay, there is also another effect which we have seen. That effect is the expulsion of the magnetic field. Okay, the magnetic field gets completely expelled of this. So, because of the magnetic field expulsion from the system, the material becomes perfect diamagnet. Okay, and this is known as Meissner effect. Okay, superconductivity has very large number of applications. Like, for example, you have medical science. The picture shows you, for example, the MRI magnet. And then you can use it for production of energy. High energy physics uses this system. Also transportation, maglev, magnetic levitation, and the electronics, for example, frictionless bearings, and the instrumentation areas require these instrumentation, like for example, squid detectors. So they can detect very small signals of the brain, etc., can be detected. Then the superconducting magnetic energies, SMES, that's another area where it can be useful for generating electrical energy. which will be useful in case the regular power availability becomes small. There are also cryogenic power lines. Superconducting lines are there. 15% of the generated electricity is dissipated in transmission lines. Potential 100-fold increase in the capacity. The prototype, for example, what they have done is 1,000 megawatts is transported in a diameter of 40 centimeters. Sorry, this much power is actually transmitted by this cryo cable, okay, or cryo power line. There can be two types of power lines depending on whether the material is belonging to a low temperature superconductor or high temperature superconductor. Okay, you call this as LTS and HTS. And for example, the various compositions are shown here. If you consider the cryo power lines with the liquid nitrogen shielded one, so you have liquid nitrogen inlet at the center, surrounded by a dielectrics, liquid nitrogen return, and again some radiation shield followed by the outer vacuum jacket. Okay, in this particular case, especially high TC material tape preparation, there are many layers, okay, many buffer stocks, and then this I think is specifically for rare earth material based boron carbide development. Okay. Now the trains, for example, magnetic levitation. I think you remember that we had a lecture on this magnetic levitation. Okay, the trains do not have any wheels. Okay, and because there is no need for touching of the train through a wheel onto the track. So the train is literally lifted out of the track, and that will make sure that the train goes at very high speed because of zero friction. Okay. This process again involves magnetism. Okay. And a set of magnets are able to attract, another set of magnets will repel. By the whole process, then the whole system will be moving at a fairly fast zone. Okay, so this is magnetic levitation is another important topic, which I think a lot of information needs to be, we have seen already in some earlier classes under superconductivity. Okay. So these are some of the experimental maglev trains. Okay, so you don't have a track, but that train is actually supposed to be well within the track. Okay, now cryogenics is also useful in high energy physics. This we have seen. Okay, large hadron collider. Okay, we have seen LHCs. Okay, under the large hadron collider, you have to accelerate the particle. You know how the particle acceleration is there. And you require, for the acceleration of the particle, so you require a tunnel, okay, in which the particle will be moving in. Okay, and now this whole tunnel, there'll be many vacuum sections which are combined together, which can be evacuated. So for cryogenics is specifically required for superconducting magnets, which are present in such systems. I believe we also need the magnetic fields so that the particle can be bent at an angle. There are people are trying to find out the particle X. Okay, large hadron collider. There are experiments which are going on in this area. Okay, and you see the cooling requirement in such cases. The cryogenic requirement is 8 times 18 kilowatt. at 4.5 K. Okay, see the amount of cooling power that's required. Or 8 into 2.4 kilowatt, which is at 1.8 K at a much lower temperature. And then 36,000 ton at 1.9 K. So you have nearly a very large quantity of helium inventory. 136 tons of helium inventory is there for taking care. So this is a large hadron collider. Okay. Now we're coming to ground freezing. So why do we freeze? If I freeze that zone, then it's easy for me to remove the material over there, and for applications of building construction, etc. So it will help to make tunnels or holes in that area. Okay, so that is the advantage. So you can see here, I think the 3D, this is the ANSYS analysis or some analysis which shows you when this blue zone is the cold zone. Okay, so this cold zone can be completely removed off. Okay, so that the pipelines become somewhat free. Okay, and the foundation, for example, you can see how it is being drilled. So the cryopreserved in some zones. Okay, and once the cryopreservation is over, then it's easy for you to remove all the central part of this, etc. Okay, this is again another photograph of the cryoground freezing. Okay, sorry. This is a one which is in the C zone, coffer dams construction. It's again within the sea area. Now coming to imaging techniques, you have two things. One is the electron microscopes and then the IR spectroscopy. The protein structure with the very, very precise geometrical shapes have been identified, and this won a Nobel Prize in 2017. So now you have a resolution. You can see in this picture the resolution prior to 2013 is on the left side, and the present resolution, you can see here how fine the resolutions can be seen. So this is another important development in the area of cryo-electron microscopes. Okay, so in this case, what you need is very special, very small energy electron beams are required, and very high sophisticated image processing also is required here. So the cryo-electron microscope, in which a beam of electron is fired at a frozen protein solution, the emerging scattered electron pass through a lens to create a magnified image on the detector, and from that one can determine the structure. Okay, so you see there are frozen samples of protein, electron gun, and then you have the lens, and you get whatever that beam comes to the other side, that gets appropriately recorded on the electron detector. Okay, there are some spectroscopy called IR spectroscopy. This was invented by Yale University professor Mark Johnson and his group. The molecules are ionized using electrospray ionization, then frozen into the stable configuration around 10 Kelvin. That means you put it there and then keep the solution, make it that around 100 K, then it becomes more or less frozen completely. It traps some of the short-lived states of the molecules. The cryogenic IR spectroscopy, ions are injected into the first ion trap buffer, and reaction gases are introduced in the second pulsed or continuously. Cryocooled ions and their reaction products are guided into the cryo ICR cell. Then they are isolated, radiated by IR laser pulses and detected. So these are some of the important information regarding cryo-IR spectroscopy. Okay, coming to machining, I hope I will be able to finish it today. There are metal working, hardening, metallurgy, cryogenic deflashing, then etching, shrink fitting, cryo grinding. So these are the various areas where cryogenics is useful. Let's come to machining. You can see in the picture some part is getting machined and this is done on a suitable lathe. Okay, when you do this, obviously there is going to be the metal working will take place because of this cryogenic treatment. Okay. So the metal essentially gets cooled. So you have to, when it is cooled, automatically the characteristic of the material changes. It becomes useful for the person who is doing the metal working to see a strong, a sharp beam of liquid nitrogen spray from a suitable arrangement is normally done in the case of metal working. Now, there are also cryo hardening and metallurgy that is possible. Okay, there are materials, you can make it harder if you have a cryogenic treatment. So it can be done for selective gears. Or for example, you can use the material property change at low temperature for certain specific applications. So these are some methods in which you can improve the properties by taking to low temperature. Okay, essentially you cool the material to 185 degrees centigrade or 88 Kelvin. And then this causes the increase in the amount of martensite in the steel compared to the original case. So now the strength increases, hardness increases. Also sometimes the cost is increasing. And this is one of the industrial methods for doing the treatment, cryo hardening using the metallurgy problems. Okay, here again you can see in the picture the treatment on tools. Okay, see, it is well known that the tools, when they are treated by cryogenic conditions, normally their performance improves to almost maybe a factor of 10. Okay, or in some cases it's a factor of 100. It's all possible to do this. Okay, a lot of applications, musical instruments, baseball bats, golf club, and then racing engines, firearms, etc., knives, razor blades, and then brake rotors, etc. Well, this is some research laboratory at TKM, the cryogenic research laboratory, experimental setup, etc., is shown here. Now, the cryogenic treatment of metals is one important area which is normally helpful. If you take a normal steel, when during the process you get a certain amount of treatment done during the fabrication. The austenite does not get fully transformed to martensite during the process. This austenite is called retained austenite. Okay, austenite. This is called retained austenite, RA. Now, when you do a cryogenic treatment, that's retained austenite turns into martensite, which is about approximately 9% of steel already. This is one of the desired conditions. So by this treatment, the voids, imperfections, etc. are eliminated. IASC, we have also developed an experimental setup. I think the setup details are shown here. I think I have shown this at some time earlier thing. So you can have a room temperature material cool down at a particular time period and then kept at the cryogenic temperature. at for a certain time period. Again, you can do an appropriate warm-up schedule for this, right? So this is the so-called cryogenic treatment setup. In the institute, for example, we already made a cryogenic treatment setup and it is running. Okay, you have a liquid nitrogen flow coming in to the system from the storage devar. It cools an upper chamber and then the vapors are going out. So the upper vapor in turn cools it circulates the gas load which is present within the chamber by suitable means. So the whole zones which is kept here becomes completely cold. Okay, it reaches the cryogenic temperature, appropriate temperature, whatever that is designated. Okay. There are effects on wear, frictional force increases. The number of newtons actually increases by almost 30%, whereas the wear, for example, for a material which is treated with the cryogenic conditions, the improvement is about 59%, and total percentage improvement is about 33%. Now, machining, if you come to cryogenic machining, okay, we'll see, for example, first we'll see the deflashing. Deflashing is where you have materials which are when you normally form a rubber component. There are always extra material which is sticking to it. That's called flashes. So what is normally done is this entire raw material is kept along with there are materials. These additional materials, for example, they are along with that. If it is cooled down, then there are some ball mills, etc. If they are cooled down along with the liquid nitrogen, then the liquid nitrogen tries to remove the material, all these flashes away, because flashes generally get cooled slower. Get cooled very fast, whereas the parent material gets cooled very slow. So because of this reason, you will see the flashes are removed as quickly as possible. Okay. Particularly, for example, there is something called cryogenic etching using a MEMS method. Okay, micro machining systems. There are very fine fusion the very fine SF6 silicon for etching it is used. Silicon is removed from the form of SiF4, which is volatile, blocking layer or oxide fluoride on side walls. Together at cryogenic temperature, together with cryogenic temperature, it inhibits the attack on the layer. Okay. So cryo temperature operation also assists in reducing the etch rate of the mask material, which is either photoresist or silicon dioxide. So you can see the way in which it is removed, material is removed. Okay, there is an important process, cryogenic shrink fitting. I think I remember having shown one video on shrink fitting. So this process is also well known. Two materials can be made to mate together. Okay, for example, bearing in a housing and similar fittings can be done using this cryogenic shrink fitting. Okay, I mean, these are experimental stations where the cryogenic shrink fitting will be done. Okay, I come to cryogenic grinding. In the cryogenic grinding, the rubber raw material can be totally ground or any plastic material can be ground. It's also possible that you can take human air and grind it into fine powder. Okay. So essentially, you are trying to get fine powder of the material. There are a number of companies like Reds, for example. They give the cryogenic grinding system they are able to give. There are also big size machines are possible to have cryogenic grinding using appropriate feeding arrangements during which the liquid nitrogen will be supplied to cool the raw material, and then it will be cooled and it will get ground by the special machine, which is grinding machine. Okay. The advantage of cryo grinding is most efficient particle size reduction. Then many tough materials can be ground. Liquid nitrogen is used for regulating its temperature. So one makes sure that the entire system is maintained at a proper temperature. And inert grinding is also possible in such cases. There are a lot of applications we have just now seen. And there are important references which are available. Kindly have a look at it. Randall Barron, then Timmerhouse, Cryogenic Process Engineering. You also get a lot more information in NPTEL lectures. So you can probably download it or read it online, etc. There are some Wikipedias and Google images, etc. have been used here. These are some of the things used by Professor Rijo. So class notes of Dr. K.K. Abdul Hamid, Abdul Rashid, etc. And website of Inox, Air Liquide and Linde Cryotech, NASA, and VSSC, ISRO, all these information has been taken from these various sources.